Hello, my name is Julian Osorio, and I will be doing the Ansys simulation for the final project for Propulsion. So, Jack, who is my partner, did the theory part of the project, and this, as you can see, is the Ansys simulation. So, we start here with the geometry, just made a base shape with the first turn at about 10-degree turn and the second turn about 11 degrees, which will give us a nice shape as you'll see later. But yeah, this is geometry. We'll close here. So I'm gonna reset everything else just to show the process. So we'll open the mesh and just let it load. So there it is. There's the shape from the geometry. And then I'll just start naming the sections. So this one will be pressure inlet, pressure outlet. We'll just name this walls. And then I'm going to name these three as far fields. So as you can see, every line is as a named section. So I'll click Insert Method, click there, click the object, and then I'm going to use this triangle method for the mesh, and I'm going to just use a 0.03 element size, which will nicely come out to this. We'll see in a second. Yep, there's the mesh, just a bunch of triangles. So we'll close the mesh. Then we'll update it. There, and then we'll open the setup window. Oh, I like to use double precision. Doesn't make a huge difference. As we wait for this to load, we're gonna pretty much just turn on the energy equation and make sure we're in a K omega for the solver. And then we'll change some of the walls to far fields and the pressure in it to a far field. So first we'll go to the energy equation. We'll turn it on. For the viscous effects, we'll turn K omega with the SST. We'll just click OK. You can close here. Go to fluid air. We're going to make this an ideal gas. Change create close. Make sure it's saved. Yep. And we can close this and then we'll double click boundary conditions. So pressure inlet, we're going to change this to pressure far field. And I had a base values just to keep it simple. Like close. That's the pressure inlet, pressure outlet. We can Yep, pressure out. We'll double click it there. And then I just put a base value of this and then apply close. The walls, we want to keep it as walls, but the wall far field will also change it to a pressure far field. And then insert the same values. Apply close. And then that's pretty much done for the setup. So click initialization, initialize, let it load, and then we'll run the calculation. iterations. We'll set 50 iterations just to keep it simple. There we go. So then we'll go into graphics. We'll make a contour, and then this is where we'll see all the graphs. So we'll start with the Mach number contour, and you could see as the first turn, you could see the wave angle of the first oblique shock wave, and then as the second turn occurs, you'll see the second oblique shock, and then when they both meet at the point, then we create a normal shock. So that's the Mach number contour. Velocity contour is going to look very similar. First oblique shock, second oblique shock, normal shock. It's a little attached, but just for the sake of the video, we'll keep it like this. Next we go to pressure. Pressure is pretty much going to have the opposite effect. It'll start low, and as oblique shocks occur, it'll get a higher pressure. Same as the temperature. You see, starts lower temperature as oblique shocks occur. Temperature increases. Not too much, but it's noticeable. Total temperature is about pretty much constant throughout, as stagnation temperature doesn't really change due to shocks. The pressure, total pressure, is going to look like this. Seems about right. Yep, as pressure recovery ratios across a shock always increases. Next we'll go to the plots. We'll open an XY plot, and then we'll just show the same one. So we'll go to velocity, Mach number, and for this we need to create a center line. So I do a point. We'll call this center line, and then select points with the mouse. I'm going to pick this and about there to get the nicest kind of values. There, create, close, and then if we click center line and we click Mach number, you'll see this. So the Mach number is constant up until it hits the first oblique shock. You can see it decreases, and then as throughout the area between the first and second oblique shocks constant. And then when the second oblique shock occurs, it'll decrease again. And then once it hits the normal shock, it'll also just decrease into, you can see this is about 1, Mach number 1. So as normal shock passes, as a flow passes through a normal shock, it'll always be subsonic, have subsonic flow. And then the same effect is going to have for the velocity magnitude. Constant until the first oblique shock, decreases after the second oblique shock, and then decreases due to the normal shock. And then we'll go to pressure. It'll have kind of like the opposite effect. Constant until the first oblique shock, pressure ratio is going to be greater than 1, so the recovery is going to increase. So then as it goes through the second oblique shock, it'll also increase, and then through the normal shock, the pressure increases. Same effect as temperature. You can see here, constant, first oblique shock increases. This is static, so this one changes, and then pressure increases after, temperature increases after the second oblique shock, and then after the normal shock. Then if we go to the pressure, total pressure, stagnation pressure, it has a weird effect, but eventually it just increases. And then for the temperature, the total temperature, it has like a weird effect, but realistically, it should just stay constant. In this, the values are so close to each other. It doesn't make a massive difference between them, but it's exaggerated when we're this zoomed in. But that is all that was asked to be shown for the Ansys simulation. Thank you for watching.